Welcome to the HiRSE-Seminar series on research software engineering in Helmholtz and beyond.
Thank you very much, Claire. I will just start sharing my slides. Hopefully you can hear me just now.
Yeah, can hear you, no problem.
Okay.
Yeah, slides, see the slides, all good.
Great. Well, thank you very much for the invitation to speak in this seminar series. It's lovely to see so many of you online, and I guess I'm all that stands between you and your summer set of testing seminars. So hopefully this is a really good lead in to some of the different aspects that will be of interest to you. You'll notice that in the title, I have added the word research in brackets there. So I'm going to be considering how software metrics can improve, in particular, research software quality. And it is a question that I'll pose through this presentation as I go through a number of different topics. If you are interested in seeing the slides are available on Figshare, either through the link that you can see here, or if you search my name on Figshare, you'll be able to find the presentation as well. So in this talk, I'm going to go through 5 different things. Firstly, I'm going to talk a little bit about the definition of software quality itself. Then I'm going to consider what that means in terms of applying software quality definitions to research software. I'm going to go on and talk about some of the different ways that we might measure research software quality. And then finally, I'm going to finish off by talking about some of the different initiatives like HAOS and FAIR4RS software that are aiming to look at how we assess different aspects of research software quality, as well as looking at some of the tooling that's starting to become available. So first of all, what is software quality? There are lots of different definitions of software quality in the literature. They're very formal definitions coming from software engineering, particularly from industry, which look at the different aspects that it takes to make a piece of software of high quality. These range from things like performance and usability to looking at aspects of the way that the software is being produced or assessed. So there are many, many different definitions. You can see some of them in things like the Software Engineering Book of Knowledge, for instance, or in some of the ISO, IEC certifications. What I want to do is kind of take a little step back and identify what perhaps each of these definitions have in common. And I would say that they all have 3 separate sets of aspects of software quality. One aspect is the functional software quality. So this is basically, does the software do what it's supposed to do? Does it meet requirements? Does it have few bugs and errors? Is it effective in terms of the way it communicates with the user of the software? The second aspect is the structural aspect, which is, does it perform as needed? So this includes things like security. Is the software, again, looking at bugs, for instance, is it free from bugs in a way that ensures that mistakes will not happen, that will cause integrity problems? Is it understandable? For me, as someone from the Software Sustainability Institute, an important part is it maintainable? And in general, is it constructed in a way that is the best way of doing it, or a good way of achieving the functional part of it? So functional and structural. There's also a third aspect, which is increasingly looked at in terms of software quality, which is less about the software itself, but more about the process of making the software. And so that's whether or not the project, the team that are creating the software can consistently deliver. Can they deliver on deadline, on budget, in a way that is repeatable and resilient? So is the development process of high quality? And these 3 different aspects work together. You could have software which does everything that's supposed to do, meets all of the requirements, but is very hard to maintain, is insecure, and cannot be delivered on time. You might have software which has a brilliant development process that follows all of the best practice, but doesn't do what it's supposed to do. So for a software to be of high quality, it really needs to be able to address each of these three different aspects. And I guess you'll be aware of the sort of rule of any two of three, where in many kind of trade-off situations like this, you get told you can have any two of these things, but not the third one. What we'd like to see when we talk about software quality is being able to meet all three, but the trade-off is around how far you can meet each of these three things, given the amount of resources that you have. So, what does this mean for research software? So software quality can be well defined, and there are a number of definitions. You can break it down into these three different aspects of what it's supposed to do, how it's constructed, and what the process of construction is. But in reality, when we look at a lot of research software, the challenge is that we don't necessarily do this in the same way that we are perhaps developing products in industry. Or another way of looking at it is we're doing it in exactly the same way as we're developing products in industry, but the incentives are different. So this cartoon from XKCD, which has a number of really brilliant insights into software development, I think speaks to me as someone working in research software and research software engineering, in as much as it's saying, you can have all of the process that you want and improve the process quality, but actually the choice of which software becomes popular, which software becomes well used, is not necessarily in your hands. And it feels like it's more so in research software. It feels that in research software, it's very hard to identify what software is going to become very popular and what software is going to fade into obscurity. But in practice, that's exactly the same in industry as well. The difference is that we never really hear about that. We only see the hits, the things that make the money, the things that are sold. It's the same in research software, except we, being part of the research software engineering community, see a lot more of the misses as well. So how does software quality apply to research software? When we look at this, I think it's important to understand that all research software is not the same. There are different levels of maturity of research software, and there are different elements of best practice that should be applied at each of these different levels. Groups across the world have been looking at doing this. There's a very good definition that's been derived from the German Aerospace Center, but I'm going to look at this particular set of 3 tiers, which is adapted from work from Tom Honeyman at the Australian Research Data Commons, who in turn based it on some of the work of Konrad Hinson in France. And Tom has basically suggested that there are 3 levels of research software development that it makes sense to look at. The first is analysis code. So analysis code is the code that is often used to support publications. It's the scripts that are used on a one-off basis to either process or visualize the results of some research, and it's then maybe used in a paper. Often, the only thing that happens with this code is it's deposited with the paper, or sometimes not deposited with the paper, and it's rarely revised after the publication. So it's really designed as something that is used by one person for one purpose. Moving a bit further down the stack, you have prototype tools. These are the sorts of things that I work a lot with, where they are things that have developed beyond analysis code, where they're being used multiple times because they have a piece of functionality that's very useful for a particular part of the research, but they're not supported in the way that a product might be. They are things that are often done with best effort maintenance. They are tools that are typically shared amongst collaborators more than being used by a wide community. And it's often called professorware here. It's the sorts of things that come out of research groups that have they're more stable and they have more users and they're better maintained than analysis code, but they're still some way off from being something that you would expect anyone to be able to come and pick up this tool from the discipline. And then finally, you have research software infrastructure. And this third level is the thing that a lot of us aspire to, where we are applying engineering techniques to create a professional product that does have support, maintenance, a roadmap of how functionality will be developed, and is something that the whole of the community can use as a platform to build other things on. And these three different levels, you could have code that starts as analysis code, moves into becoming a prototype tool, and finally becomes research software infrastructure. You could have software that started off as an idea for being research software infrastructure and was immediately built using those kind of techniques. You can have software that combines all three different types of code. When you think about the way that people use platforms like R or SciPy, you could consider things like SciPy to be the research software infrastructure. Quite often within that, there may be libraries that integrate with it that are prototype tools. And then finally, there'll be a small piece of analysis code that's written for a particular paper. So our challenge with software quality is that often we are talking about different levels of maturity of the code, and that code of different maturities may be integrated together in any one application of a set of software. So what is the problem that we are seeing here? I think one of the big challenges, and certainly it was about 15 years ago, is that there was this feeling that the scientific community and the software engineering community were somehow very disjoint. They were doing things separately, they were doing things in different ways, and they weren't really learning from each other. Of course, this quote is coming from Diane Kelly, who's a professor of computer science in Canada, and it was based on a result of looking at across lots and lots of researchers who are working in software use and software development. But as I said, this is now over 15 years ago. And what's happened since then? We've had the research software engineering movement, and we've had a whole set of people really think about what does it mean to do software engineering for research software. And we're starting to see that the communities are coming together. I co-run a workshop series called Software Engineering for Science with Professor Jeff Carver. And what we are seeing in those workshops is the two different sides, the people, particularly from the large laboratories where they are maintaining research software infrastructure to quite high standards with large, well-resourced teams, are applying a lot of the techniques that are coming out of the software engineering community. But likewise, what we're seeing is more people from the software engineering community, particularly the empirical software engineering community, consider what makes research software different and understanding how some of the things that you might naturally apply in industry need to be adapted to be applied in the scientific community. So what do I think is the way that we adapt the definition of software quality to be more usable for research software? So I think at one level, what we've got to understand is that the process of development of research software is slightly different. And it's got this issue in that sometimes we don't know exactly what the requirements are to start with. We will know some of the requirements around the way that someone expects to use the software, but we might not have the same understanding of what is good or bad performance, for instance. And so I break down research software quality into re-examining those three aspects as follows. I think functional research software quality is about whether the software implements the algorithm or simulates the phenomenon as expected. So if you are trying to do something, does it do what it says in the bit of your paper that describes the algorithm? For structural research software quality, it is still very much the same. Does it perform as expected? But in this case, it might include things like, does it scale? Can it be parallelized or optimized for different platforms? As well as being maintainable and secure. And then in terms of the process, I think it's very much similar. Can the team consistently maintain the software and deliver new versions and products? Can it incorporate the different requirements that are coming in and feature requests from the community, and identify a way of best satisfying all of the requests that are coming in from a piece of software? So that's how I define research software quality. It's not very different from the definitions of software quality because research software is software. So the question then is, how do you measure it? And that's where it becomes potentially a little bit harder. So there are different ways of measuring things. You'll see terms like static analysis and dynamic analysis, and each of these refer to a different way of potentially measuring the quality of software. So one way that a lot of software is measured by is using code metrics. These are things that look at, for instance, statistics around the complexity of the code. So how large are your different functions in comparison to the overall size of the code? You can look at things around how often code is being changed or updated. You can look at things like test coverage and so on. But some of these things are quite hard to apply for research software. The one that's normally brought up is test coverage. So there's something that is known as the Oracle problem. And this is where to put in particularly unit tests, you really require to understand what the correct answers are. What is a valid test? And sometimes the challenge here is that if you're doing exploratory code research, code development for research, and that's particularly when you're working with analysis code or prototype tools, you might not necessarily know what you're looking for until you found it. And so one thing that's really important, I think, is that research software metrics vary depending on which software tier you're in, whether it's analysis code, prototype tools, or research software infrastructure. And many of the things that you see in the literature around software metrics for industry are really only applicable to research software infrastructure. Another set of things that you can look at are project metrics. And so project metrics include the way in which the software is being developed and the teams that are used to develop it. You may have heard of something called the bus factor. The bus factor is a measure of reliance on particular key team members. It's basically how many people would need to leave your team before you would not be able to still understand how to develop the code or project. Another one that is less commonly known but is very important in terms of research software is the elephant factor. And that came out of work that was done in the open source community, and it refers to the number of organizations that are contributing to a piece of software and the ratio of developers to organizations. And what that kind of means is that if you have one organization that has the majority of the developers on a piece of software, it can be it can be sort of fragile to change, because if that organization decides no longer to be developing that software, you lose a lot of the developers in the team. What has this got to do with research software, you might be asking? So one of the phenomenon that we see that applies to elephant factor with research software is quite often research software starts off as relatively small scale development across a number of volunteers. For instance, it might be a research group and then the collaborators that they have across the world. As that software gets more popular and it gains funding, what often happens is that you will have a single group getting funding that is then used to create a development team and pay them properly. But that centralizes the developers all into one organization, or certainly being funded from one grant. And at that point, you start having fragility, because when that grant finishes, what happens to the software team? Does it then mean that the team members going back to becoming volunteers, or being paid by their own institutions, or having built up the skills in this project, do they go on to do other things and go off elsewhere? So I think it's a very important project metric for research software. And then there are other things that you can look at, which are around the interaction of a project with its community. A very common one, for instance, is issue response time. And that's something that is a real marker for, as you go through the different tiers, as you get to research software infrastructure, is whether you're considering metrics that are around how you interact with your community. There's possibly a third set of metrics as well that apply specifically, or certainly more commonly, to research software, and that's around producer metrics. And the reason I say this is because in many cases, in the general software development world, what people care about is more whether the piece of software they're using, whether that's well built, of high quality, and does what it needs. In the research world, there's a lot more around track record and reputation. So people will look at a piece of research results and apply a quality rating based on the people who are developing it. And so perhaps here, the research software world is more similar to the game development world, where more is placed on who's producing the piece of software than necessarily the quality of the software itself. Okay, so I'm now going to kind of move on and talk a little bit about what's been going on in this area, and how this sort of way of looking at research software quality and research software metrics applies to the way that people perceive software. So one thing that we did at the Software Sustainability Institute a few years ago was try to do an exercise to understand how successful research software is perceived. We did this by looking at a selection of different pieces of research software that had been identified by another project, and asked respondents to categorize what they felt was successful versus unsuccessful software, and give reasons for why they felt it was successful. And so these are the sorts of things that come up as potential indicators for why people think software is successful, and by proxy think of as being of higher quality. So this is less quality as being understood by the developers of the software, and this is now research software quality as being understood by the users of the software. So some of these are what you might expect to see for most pieces of software, which is around things like documentation, the number of contributors, the number of users, how regularly the software is being updated. But some of the things that were particularly important for research were things like whether there were related publications, citations, data sets. So how well linked was this software to the work it had created and impacted? That's also the case in terms of looking for things like case studies, examples of real life use. So often this is from looking at the way that software is advertised. For instance, most people, when looking for a piece of research software, will either use a search engine like Google, or they'll have seen a piece of software being used as being presented in a conference or in a journal paper, and they'll want to see whether they can reuse that software themselves. In terms of things that are particularly interesting from a research software perspective, I think one of the challenges that we have in research software is this idea of hidden software, in that a lot of the software that's used in the research field is not openly published. It's partially published. So you can find references to it in papers. You can find some parts of it perhaps on a repository like GitHub, but it's not published like a product. And that can be very difficult to understand the quality of software as a user. And I think the second thing that I'd like to highlight is that in a lot of cases, it's less the I guess it's less an understanding of whether the amount of effort that's going into the project is of high quality itself. So are the team members good at their jobs? But there is more around how people see activity. So are they being responded to? Are they seeing that bugs are being closed, that issues and requests are being answered on a regular basis? So there's quite a lot of different things that might be indicators of how people view high quality software, but a lot of them are really more around the process of how the software is developed more than the accuracy, which is really interesting. So what does that mean? I think it means that overall we can look at 5 different sets of measures that are around understanding whether research software meets the quality definitions both as a developer and a user. And I call these the PRISM measures because of the first letter of each of the categories. So I think that a good way of looking at how you might assess research software quality is first of all to look at whether it's portable. So can software be run on different platforms? Perhaps is it available in different languages? A second one is around reproducibility. So does the software help support the repeatability of experiments that are using it? A third is interoperable. Can the software be used within a larger ecosystem of software? Is it possible to make sure that it can be used with popular data formats? Can it be combined into workflows? Is it scalable? So can it handle different increased problem sizes efficiently? Can you use it for larger and larger pieces of research? And is it maintainable? Can it be easily modified to correct faults, either a small tweak by someone who's using it, or is it being well supported by the team that are developing it? And finally, around maintainable, can it adapt to a changing environment? So when we spoke about software sustainability, we often talk about, can the software continue to do what the user needs it to do as everything around it changes? And in particular here, what we see is that hardware refreshes happen on a relatively regular basis, maybe every 5 to 10 years. And we see many more other changes that are quite rapid in the way that other libraries are developing and operating systems update. So those are the sort of 5 categories of what I think we should be measuring to understand research software quality. So I'm now going to talk about some of the ways that people are looking at this. One initiative that I think everyone should know about is the CHAOSS initiative, which stands for Community Health Analytics for Open Source Software. Whilst it is coming out of the open source community, it recently has had a research software metrics group start up here. And what CHAOSS is looking at is really around the product metric, the process metrics. So it is looking at a lot of different aspects of how the software projects run and how the team organize themselves and ensure that they are in the best possible place to put in the best practice on the functional and the structural quality aspects. So the way that CHAOSS works is that it has a number of different contributors from all around the globe, most of them working on very large open source projects. And they talk about how to define metrics for a number of different categories. So you'll see some of the ones listed on this slide are around things like community metrics, where they're looking at how you measure the people who are working together and how well they share goals, for instance, or things like governance and leadership, so how are decisions taken. They do, however, also have some metrics that go down towards the individual pieces of software. And so if you look at the software metrics group, they have a number of different things that look at how you might analyze particular pieces of software to understand their quality. So that's one side of it, the CHAOSS project, which is around standardization on the metric definition, so that they can publish something which is effectively a framework that other people can then go ahead and use. And what that allows people to do is develop tooling. And so this is a tool called Grimoire Lab, which is a dashboard system that allows open source projects. You can connect repositories to them, and you can apply some of the metrics that CHAOSS have been developing directly to the repositories. And so this is for anything that is possible to be written as a sort of static analysis code metric. And so here you can see a dashboard that is looking at some of the repositories that are part of CHAOSS themselves. The second thing I wanted to talk a little bit about is the FAIR for Research Software Principles. So the FAIR for Research Software Principles are based on the existing FAIR for Research Data Principles. And what they're looking to do is extend the FAIR principles from data to software. And indeed, there are now many other groups that are looking beyond FAIR data and FAIR software to FAIR workflows, FAIR AI models, and so on. And the idea of the principles is to give some guidance and direction for what you need to do to make your software findable, accessible, interoperable, and reusable. And whilst that's not directly related to software quality, there is a very strong overlap in terms of what the FAIR principles are looking to do and what a number of the measures for research, for software quality and for research software quality are trying to do. And so I think it's important to understand perhaps how the FAIR principles mesh with software quality. So some of the FAIR principles are really around documentation, findability, metadata. So you remember I put up the slide around the pilot study, which said that most of the aspects of what makes a project seem successful were around the way it was documented. So likewise, the FAIR for Research Software Principles have a lot of different principles which are around how software is documented with metadata and identified with identifiers. Another aspect which came up in the way that I classified the PRISM set of software measures is around interoperability. And in particular, that in FAIR for Research software, you want software which can read, write, and exchange data in a way that meets domain relevant community standards, and in effect allows integration with other pieces of software which are commonly used in any particular discipline. And then finally, the R in FAIR for Research Software Principles is that software is usable and reusable. So here, this is really coming to the aspect of productization of software. So as you go down the different tiers of software, from analysis code to prototype tools to research software infrastructure, that software becomes more usable and more reusable. And there are a number of different ways that can be applied to do this, from making sure that it has a clear and accessible license to making sure that it is well described. But then a lot of things are encapsulated in this last one, R3, that software meets domain relevant community standards. And what we see now is that many domains, for instance, the geosciences, are coming up with coding guidelines for how software should be developed to meet the different tiers of maturity. And following on from the FAIR principles, what we're now seeing, although it is still very early days, is we're seeing tools that will allow us to assess software fairness. And many of these work in the same way that Grimoire Lab works with the chaos metrics, that they could be applied to a software repository, and they'll give a list of different things that could be improved in that software project to make it more fair. However, there's still a lot of room for improved functionality here. Most of these software tools started off as being applied to data, and it's only recently that they've started adapting to be used for research software and for the FAIR4RS software principles. But there's a lot of work going on in two EOS projects, FAIR Impact, which I'm a part of, and also FAIR Core for EOS, to develop these different tools and to evaluate how usable they are themselves. So in some sense, we're looking now at the software quality for tools to measure the software quality. It's all getting very meta. Anyway, I'm going to kind of wrap up now and give some time for some questions. I think the sort of message I'd want to leave you with is that the difference between research software quality and software quality in general is really about the incentives for why the software is being developed, more than the way in which the quality can be measured and identified. There are a lot of initiatives in the community about creating metrics that are more useful and appropriate for research software. The key group here is the new research software metrics group in Chaos. That there is tooling, but that tooling is still quite immature and is developing. However, there's a great chance for people to be involved in providing feedback and making that tooling better. And then maybe going back to that original question I asked, can software metrics improve software quality? I guess the question can be turned around and put back onto you, which is, do you think software metrics can improve software quality? Because as far as I'm concerned, yes, maybe they can, but maybe not always. And so a lot of it is really about where you're trying to apply those metrics. And I think we can apply software metrics to improve software quality for research software infrastructure, but we still have a way to go to understand what are the things that help improve software quality at all three levels of research software. So with that, I'd like to thank the huge team of SSI staff, collaborators, and people that have been working in this area, and our funders at the UK Research Councils. And also just to sort of say that none of this can be done in isolation. I know that you've had a lot of brilliant talks in the seminar series. You'll see that so many of these different topics are related to each other. So thank you for listening. Thank you to all of the people who've helped contribute to this work. And I'm happy to take questions.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below and see you next time.